our next speaker is David Cerf with GRAU Data, a brand new consortium member. And his talk is entitled Optimizing Data Management for AI, the Synergistic Role of Metadata-Hub and iRODS.
Thanks, Corey. Can everyone hear me? All right. So I'm David Cerf. I'm the Chief Data Evangelist at GRAU Data. We're a 20-year-old software company based outside Stuttgart. So we're in Schwäbisch Gmünd for those in Germany. And what I'd like to cover is three key points in today's presentation. The first is the critical nature of embedded metadata, how it's going to change and drive our data-driven world, and how it works with iRODS. First, I'd like to clarify the metadata word. It's very much like the way we use cloud. We throw metadata around a lot nowadays, and I want to make sure that it's really clear what we're talking about is embedded metadata. So we just heard a talk on metadata, of course. We're all used to POSIX metadata because it's how we're driving most of what we do in our file systems. So it's age of file, last access, et cetera. But embedded metadata is actually the metadata within the file, so it involves opening the file. And that is where the challenge comes in, because what we're dealing with in our machine-generated world is we're creating lots of files that have very complex metadata structures, and the metadata itself is the critical value within the file. So in this case, we're looking at a genomics FASTA file on the left, and you can see it's machine-generated. Humans aren't going to really read this. On the right is the extraction of the embedded metadata to make it usable. What we're finding is that almost every data-intensive application requires this type of embedded metadata. So to make our analytics more effective, there is no AI without embedded metadata, certainly not machine learning. Anything that's going to be related to discovery is going to require workflow automations, and certainly the integration back with data orchestration, which is where this comes in with iRODS. And so to support and drive machine learning and AI, we need to have a workflow that allows data to be available and accessible all the time. And hence lays the problem with the embedded metadata, is that most of the files are sitting up in expensive primary storage because they need dynamic random access. And so this change that we're seeing around these type of machine generated files is it's the majority of all data being created going forward. So when we think about it from a volume perspective, it is in most cases for data intensive businesses, organizations, it's 98% of all volume generated that's taking up your storage. And as I mentioned, it's not meant for human consumption. So we're trying to get that into computation. And that means it needs to be available, accessible. So when it's generated, it might hit a high performance tier. It's coming out of the machines that are generating it, such as microscopes and telescopes and sensor data, and it lands in that primary storage, and that is expensive. So we might create copies, archiving, if you're doing any tiering where you're moving that copy from a primary tier to a tertiary or less expensive tier, but typically that file is still sitting and consuming your primary storage, and there is the problem. So Metadata-Hub, which is created by GRAU, we started this about 5 years ago. We're commercially viable, working with several large customers here in Europe, which I'll discuss in the use case at the end, is unique in the way that it is able to connect to any data store and extract the embedded metadata to make it into a structured, usable form for all your computation and applications. Of course, iRODS is, in our view, an application that we're able to integrate, and that makes it usable. We support over 500 unique file types. Our IP is actually a unique dynamic platform for actually creating extractors. So that's what we specialize in, is being able to work with complex or proprietary file types. And because when you work in a vertical, you need to be able to go deep. So if you're in the life sciences, you can't have a microscope. You need to support lots of microscopes in genomics and everything else that they're touching, because the desire from the user is to be able to look at across all data types to be able to accelerate discovery. So this is how Metadata-Hub implements in an environment. We run as a Docker container local to the storage. So whether the storage is in the data center, in the cloud, on the edge, we're going to connect to that physical storage. So there's your filers and the object stores, and we'll start to harvest. We have a read-only access, and we'll just go through and we'll start harvesting all of the metadata. So that includes the POSIX, the object metadata, user-generated data, and of course, opening the file and extracting the metadata. We actually create the decentralized metadata platform, or DCMP, which is the ability to support a data mesh architecture. So we have a distributed architecture that allows data products to be generated to service to the data users. So data is owned and maintained by those that have generated the data. We actually honor and help support any of the ACLs and permission access. So in the blue box is all the metadata hub that's running inside the Docker. Then those are distributed based on the environment. And then it services and feeds the metadata back to the data users. So that's the applications, that's the reporting, that would be any of the users. It can come back through browsers as well, data tools or iRODS. And we have a Python SDK, a GraphQL API, CLI, and then the browser user interface, which we'll see in a moment. So let's look at an iRODS implementation, how it works. We have data that's being generated by the machine generated sources, or any source. It's not limited. We do support any unstructured data files because every unstructured data file has metadata. But in this case, this is specific to the thing it's consuming all your storage, and that is the machine generated data that is created and hits the performance tier. So then iRODS would then tier and move that off into your archive. Except for at the point of the file creation, we can harvest the embedded metadata. So both on through cron jobs going back in and scaling our initial harvests, we're going to capture all that metadata, and that goes into the metadata hub, which then becomes like a proxy. So the file can now be instantly moved down into the archiving tier and removed from the primary storage. So if you're already doing archiving or active archives or tiering, this will actually improve it. If you're not, this will enable you to do to actually start to tier it and move that data that typically sits in the performance tier out of it. So in a use case where you may already tier, you can improve your data on the primary storage by 25 to 75%. So that's the ability to get that file to where it's not typically, will move off into the archive, because once the metadata is removed, that file is typically never recalled again. If it is, then it can be recalled back by iRODS and brought back to the application. But the majority, like 99 point whatever percent, it is going to be serviced to the data user through the metadata hub. So you're getting performance improvement in the storage and in the network. Because when you think of metadata, in the worst case scenario, metadata percentage to a file size is a minimum 1,000 to 1. In most cases, it's even going to be more significant, add more zeros. So it just depends on the file type, because you could get into things like oil or gas or certain large files and weather. Those could be in the terabyte size files. So it just depends on the file size comparative to the metadata, of course. So at this point, now the data users can access metadata directly through the metadata hub. It can be fed in an automated workflow to provision those tools directly, so there's no latency, or they can be queried, data sets can be generated, lists can be done. There are a lot of different ways it can be served. Just in case you don't happen to have an archiving backend, GRAU also has another product called Extreme Store. And Extreme Store is an S3 front side to tape. So basically, this is the ability to create an on-premise Glacier. It is 100% compatible to Glacier commands. So if you're used to writing up into Amazon Glacier, then it's quite simple. But it works with any tape library. So it's a software layer that sits up in front of the tape and disk and presents a very simple, easy to use archiving option if you need it. So let's look at this, the quick architecture. How does this deploy? So iRODS being the primary data mover and manager in the system is communicating directly with the metadata hub, whether it's one or multiple of our cores. And metadata is being back and forth in real time here. And then the metadata hub is able to go back through to any of the storage, again, regardless of where it is, and harvest that metadata constantly directly from the storage. But users can actually also create user added metadata, and we'll talk about some of that in a second. So it's going to capture and maintain everything, ensure its provision, and then if there was an archive, you'd have the archive back in here. So some of the additional features from the Metadata Hub include reporting. This creates a very unique opportunity to be able to visualize metadata that typically has been difficult to get to. So what we're looking at here is just the ability to put the metadata related to the POSIX file system metadata and the object metadata into a data landscape report. So you can see everything you happen to have across all your storage, not just within iRODS, but if you're using anything else, you can connect to it and generate reports so you can see how you want to manage it and provide real transparency. Let's take a look at that real quick. So this is just a sandbox running with 100 gigabytes of data. It's a very visual tool. It's basically going to present anything you want in a graphical form. So you can set up different types of views. You could do it through pie charts. You could do it through histograms. Everything is a drill down, so you can click into it and see that. Sorry about that. There we go. And we could see the data that makes it up. We could drill into the sources. We can create elements that are saved and maintained in our dashboard right here. And so we can create elements of saved templates and formats, view that. We could see the variations in the shares, et cetera. I'm not going to spend too much time trying to go through this. I am doing one of the talks at 4 o'clock. So if somebody wants to see the demo, please stop by for that, or you can contact us when we dive in deeper. So the idea of the reporting is just the ability that you have captured all this information. How do you want to visualize it? We can provision this back to any existing reporting tool as well. So if you already have a tool of preference, feel free to use that. Then we've integrated AI. So we support multiple LLMs, or today we can also add additional LLMs. But the idea is that we want to help the user is understand and better utilize the metadata. So the first AI implementation is what we call the metadata advisor. This actually goes in and helps describe what is the metadata. So when you have a file that's very, very large, you might have 500,000 metadata tags. Most users are not going to know all of those tags. So this can actually help the user be able to go in and understand what that looks like. So let me go ahead and just give you a quick idea. This is just going to run very quick. This is the front end of the user interface of the Metadata-Hub. You can do a natural language search, which we're doing right here real quick. It's going to bring a result set back, a list of files. We're going to click into one of the files, and there's all this metadata. This is a fairly small file. It only has 40 metadata tags. We're going to cut and paste those metadata tags that we don't understand, open the AI function here, and then drop that in. So it's just a cut and paste through the browser in this case. And then it will bring the result set back and explain it. Now, this is a one-off where a user is doing it through the browser-based UI. All of this is scriptable. So either through the CLI, the API, or the SDK, it can be automated so you can generate lists. And in those lists, it just say, go back and describe the following metadata fields. So the ability to create this across large data sets is what it's designed for, handling hundreds of millions and billions of files. So the additional metadata, or excuse me, the additional AI that we do is the ability to describe the file itself. So when we get into media files, audio, video, or imaging, a lot of times, since these are machine generated files, not expecting the user to go back and look at it, and there is no human usable metadata. So now we can apply AI back on the file to go back and describe it. So in this case, this is a microscope file. And in this case, the question was, hey, describe the file and compare. And so this brought back a result that is then generating net new metadata tags that can then be searchable and improve usability for the discovery on it. So the ability to bring that AI in makes makes it easier for the users to better define what the metadata is and to bring it into their existing workflows for discovery. So let's look at two of our customers. The first is SUSE Institute. We started with them working in their life sciences group. They had multiple different machine-generated systems. So they had microscopy, genomics, et cetera, nifty files, which were generated by brain scans. And the customer wanted to be able to utilize a comparison across all different types of files to be able to get back in and identify discoveries related to the research. So what we were able to do is connect back to the store, extract all the metadata, and then put it in a simple, easily usable form for them. They did need to maintain compliance and security, as well as meet fair practices. So the ability to share and have it readily available, et cetera, to meet grants. So all of those were requirements as for the customer. And so the result was that they immediately upon the extraction of the metadata, everything was available and accessible to the user. So they were able to reduce data prep time on the user side by over 90%. They're also, of course, able now to have transparency into the physical data itself from a storage perspective, and it made it easily accessible and usable to provision not just to one of their groups, but across all of their groups. And there are ways to use the metadata hub to actually improve collaboration. So selectively choosing what can or how to share. Other data, once we started in the life sciences, it expanded. Now it's used across the entire organization through all their departments. And so additional data for them included weather data. And one of the challenges that they had was with something called a GRIB file. So a GRIB file is just a very large weather data file, both in size and the volume of metadata. So you're at about 500,000 metadata tags per file across tens of millions of files. So that becomes very complex. Their challenge was to try to build the extractor. We were able to build that within days for them. So they had spent a lot of time and trying to do it themselves. And the difference is that the platform is able to automate this and create files for these unique use cases and tools. Same with computer vision. So in drones and autonomous vehicles, tremendous amount of volumes of data that are going to be kept forever, and you never know when you're going to need it. That ability to go back through the video file, be able to extract that metadata so it could be usable and taggable and accessible. The next use case was with Max Planck. So Max Planck was dealing with telescope data from Hubble and James Webb. So again, very large files, very large data sets. This is, our system is not really scaled against petabytes. Almost all our customers have very large volumes in excess of hundreds of petabytes in many cases. We are really measured by file count because everything is a file open. So we can handle billions of files, and that ability to bring transparency back in the files was their challenge. They had billions of files, couldn't find them, didn't understand where they were, could not make it easily usable. So by adding the metadata hub, they were able to immediately organize, access, and provision that back to the users across their data sets. The last thing I'd like to just show is the metadata hub front end. This again is the administrative UI. So when you first open it, you'll see all your different nodes. We're looking in one node, again, just due to time. And so we see some quick data around the system. We could see how many files have been harvested. Are we in a state of harvest or not? So that's a binary function. We can look at some quick stats on the data itself. So we can see MIME types, file types, et cetera. So just some simple information that the user may want to have at their hands. Let's just look at the searching. There's more advanced searches, which are compounded Boolean search capable, and these can be automatically built. So we have a no code, low code behavior for a general user, and then more advanced users can come in and script, and I'll show that in 1 second. So when we look at a search, I'm just going to do a search on the letter C, but you could make it more complex. I'm looking to get to a file that's interesting. This is a FASTA file, and the reason it's interesting is just it has a lot of metadata. If it'll open, there we go. So this has 459,000 metadata tags. And so this gives you an idea of just the complexity of the type of data that's being generated by the systems like BAM, et cetera, or converted back into FASTA, et cetera. So this metadata here can be saved. We can export it in multiple formats. We can look at the various details in it. These can actually be saved in a query as well. Let me just jump here, and I would say, let's say I want to look at the query. I just hit the GraphQL editor. We could see the query condition here. I can even send it over to our embedded editor, and we could start working and editing. So let's say that we get close to the query that we're looking for, but we want to manually edit it, we can. But again, we can keep this very simple to where we just do it in natural language search. So again, I'll demo more of this later on. I do want to respect everyone's time here and leave it open for questions. Before I do that, I just want to point out oops, sorry here. All right, so just kind of wrapping up and closing here. So what do we help do? We help reduce costs and help improve in storage. We decrease network traffic because we're removing the file itself as a query and the transport and bringing that down to the metadata level. Helping reduce prep time by the data users themselves. And we're making the data immediately available for all your applications and tools. So at the end of it, everything comes down to just faster time to results. That's really the end game. For those that'd like to learn more, my contact details are here. And also Nina Mangold, who's out of our office in Schwäbisch Gmünd, is here in the back of the room. So feel free to contact us. happy to take any questions.
Any questions? Mike?
So obviously you're harvesting
Mike.
large data sets. Damn mics. So obviously you're harvesting large data sets and you're collecting all this metadata. Is there any reporting on coverage of the metadata so that you could possibly use it to look for anomalies, malformed data, so you can isolate them from the results?
So we don't do analytics. The reporting level that we've brought is a tool just to be able to visualize the metadata itself in some form, because otherwise what we found is we're a big repository and someone's got to stick a tool on it, and configuring reporting tools for like storage reports isn't what a lot of the packages do. So we brought the reporting that we do more from a convenience, from a storage, but the comparative, the analytic elements, et cetera, along that line, typically you would have those tools like Jupyter Notebooks or data lakes or something, and we're provisioning the data into the tool that you may already be using.
So you should get the results of the metascan, and then you can report on that, but you don't do that in flight.
Right. Or what we're doing is that we're literally extracting the metadata and sending it directly into the tool, for example. So if you have a data lake, you're using Snowflake, Databricks, or whatever else you might have, Google Cloud, who cares? Any of those tools, we're just creating a data pipeline so we can downstream the data directly to it as well. So you don't have to come through us to look at it. Our function is to extract it, make it available. You can view it through us, but most of the time you're going to use it, access it through whatever you're already using, which is where you need the metadata anyway, right? Please do.
Any other questions?
Any other questions?
First of all, I'd like to congratulate the conference for making it to day 2 without mentioning AI. But I've got actually quite a lot of questions for this, but the first one really is, what's the pricing model? Because we've got near 1 billion data items just in iRODS. So if you're charging it per terabyte or per data item, that could get very expensive quickly.
So we license against our number of hubs. So the number of instances we need to deploy, and the mileage varies on what the hub can do, because it's really just housing the database. So it depends on how much metadata times the number of files, and then its size. So one is we have university pricing. If you want to talk after, I'm happy to help with that. But we developed this with institutes here in Europe. Our goal is to really help enable that, and we found that the way we've been able to bring value back to the Institute, they've all deployed it across their entire org. So they started in one place. So we've done something right, and happy to talk to you offline. But it's not on terabyte and it's not on per unit, right?
You can ask one more if you have one more.
I've got quite a few, more than one more, but I'll ask one more, which is, how does the iRODS integration work with that? So is it iRODS aware? Because with things like resources and replicas and things like that, you can have the data moving underneath kind of thing. So I can see the model where you have the Docker container running on every consumer. But then if I saw one of the screenshots, you've got it showing the location of where the file is. If the replica moves around, you move it through tiering or whatever, how is that updated? How is that integrated?
So iRODS would give us a notice that the file has been moved. So we're handing the list back to iRODS saying, here are these files, and if they need to be moved based on the policy from the list that we're generating, then iRODS would execute that against that list. If the file moves, then we get the update back, and I'll leave Corey to maybe talk more deeper hands-on. But the point is that if the file moves from the prime or any location, we're getting the update, or we'll catch it in the scan. So in the cron job, we're going to go back, but what we like to avoid is unnecessary reads, because if you're dealing with billions of files, the initial harvest is going to take the heavy load. The daily updates are pretty lightweight, because you're not changing a large enough percentage of anything that it's going to be relevant. But there are certain file systems like BGFS, ZFS, and others that can actually also do those updates, and iRODS would also update it. So that way we just try to take as much unnecessary noise out of the system as possible. Good question, though. Anybody else? I'm here afterwards, so feel free to come up and chat. Thanks very much.
All right.